My name is John Higley. I grew up on a dairy farm in Indiana, and I live in New York City for the last 40 years, 50 years. I became aware of Bucky Fuller in the 60s, 1965, while I was a student at the New York Studio School. I started reading his books and started building structures, tetrahedrons, octahedrons, whatever. Then I started using transparent paint to paint polyhedra constructions. And I eventually found out about the Synergetics Collaborative after attending the International Symmetry Festivals in Budapest in 2003, 2006, and I met CJ and some of the people from Synergetics Collaborative here in 2009. Stephen Metcalf, Stephen's sculpture was in front of my painting at the Waterman Gallery. Then after the 2009 Synergetics meeting, Stephen came to New York and he stopped in to talk to me. And I showed him some drawings of the IVM that I had done in a structure, a very crude, simple structure of the IVM that I'd built. And I asked Stephen if he'd be interested in helping me build a real isotropic vector matrix instead of the little model or the drawings that I'd been doing. And he seemed pretty interested in doing that. He's a talented sculptor, and so we set out a plan, and Stephen did most of the work because I run the preschool, and Stephen has this beautiful farm out in the country here, and with a great shop. And so this morning I thought you've probably all seen the IVM in the courtyard here, so I thought I'd show you a little bit of how it developed. This is the drawing that I did. I finally learned how to do this, how to draw the isotropic vector matrix by studying figure 98261 in Synergetics 1, which came out in 1976. And Synergetics 2 came out a couple years later, I think. In Synergetics 1, figure 98261, you see this drawing that you see up there is looking down into the isotropic vector matrix. And in Synergetics 2, there's in the color plates, there's a color drawing of a front-on view of the IVM. And the difference between those two views, I found, was the proportions of height to width. The proportions in this drawing are 8:7 height to width, and the other drawing from the front of the IVM in Synergetics 2, it's 7 to 8. 7 units high, 8 units wide. And when I figured out the relationship, the proportional relationship of these two cubes, I was finally able, after about 10 years of study, to draw the IVM. So I was really happy about that. And about the same time, while I was at graduate school at Bank Street Graduate School of Education, I built this model, a very crude model with plastic hubs and yarn from the nursery school and wooden dowels. And even though it was very crude, I seemed to be able to get it together well enough to communicate to Stephen, at least, how it was built. And this shows the first, Stephen's first attempt to build the IVM. He started with a small cube, and you see the crisscrossed tetrahedron vertices across the exterior faces of the cube. The two tetrahedrons called the duotetrahedron. And the winter of 2010, I think, is when Stephen started building this. There were 3 nor'easters that winter, and Stephen was working in a basement that wasn't really heated, and it was. I came up several weekends whenever I could to help him, and I was amazed that he could move his fingers in this. Sometimes you can.
How many socks and shoes you need?
Yeah, I kept trying to bundle up, and no matter how many layers of clothing I put on, I couldn't keep up with Stephen. He was, and you can see the ice balls here. Those are raindrops, I guess, but if you look carefully, you can see ice on the surface of these aluminum vectors. And here, the rhombic, you can see the rhombic dodecahedron being formed. The quarter tetrahedrons that fit on the 8 faces of the octahedron that form the rhombic dodecahedron. So we've got the small cube with the crisscrossed duotetrahedron across the faces, the octahedron, and the beginning of the rhombic dodecahedron. In 1973, he pursued graduate studies in urban design at Harvard, earning a Fulbright scholarship from 1973 to 74 and graduating with the MA in architecture in 75. 74, he worked with Buckminster Fuller and Sato Incorporated in Cambridge. Founded the Edward Suzuki Associates in 1977. In recent years, he's been a visiting professor at Rhode Island School of Design here in Providence, Rhode Island, and visiting critic at the Graduate School of Design at Harvard University.
Thank you, and good morning, everyone. My involvement is with the vector equilibrium, and I used it as a base for my model of the structure of the atom. Incredible as it is, quantum mechanics, which is said to be the most successful theory in physics to date, only describes the structure of the atom as a very ambiguous electron cloud, and no more, no less. Because of the uncertainty principle of Heisenberg, which stipulates that the speed and the position of an electron in an atom cannot be measured simultaneously accurately. However, that doesn't necessarily mean that there is no orderly structure in the atom, considering that the macroscopic world that we live in, which is orderly, even in chaos patterns, the atom is the basic module that make up our macroscopic world. And so I said, even if we cannot measure the positions of electrons in an atom, there must be some order in the microcosm. And so I went to try to figure out, discover what that order might be. Being an architect, I approached the problem as an architect, architecturally and structurally. Now, this first slide is my basic atom structural model. Basically, this is a cube, but as you can see, there are two tetrahedra inscribed within this cube, one black and one white. And the balls, the white and black balls on the outside represent electrons. The central gray is the nucleus. Now, basically what's happening is that electrons being of same charge, negative charge, they repel each other. Whereas the nucleus, which is a positive charge, attracts the negatively charged electrons on the periphery. So basically, these lines or vectors that run through the nucleus in the center, so all these lines, diagonal lines running through the nucleus are in tension and holding the negatively charged electrons on the outside. Whereas all the peripheral vectors on the outside are in compression because these negatively charged electrons repel each other. So basically, my model is a very simple one, almost naive, but that's where I got my encouragement from when Bucky said they are to be naive. Now, so basically, the atom is a structure imbalance. And I chose the vector equilibrium because, as the name suggests, all the vectors or the forces within the atom are in balance. They are in balance in terms of compression and tension, positive and negative charges. And what I assumed at the start was that the electrons in any atom, the pairs of electrons are in a line relationship because being both negatively charged, they want to be as far apart from each other as possible. So we have a maximum 180 degree of separation between each other. And so basically, even though it may be in motion, in dynamic motion all the time, the paired electrons in an atom are always in this line relationship. And Pauli's exclusion principle stipulates that there can be only two electrons in an orbital of an atom. So I assume that all these paired electrons in all atoms are in this line relationship. Now here's the most basic three-dimensional structure of an atom, and this is the case of carbon. I chose the vector equilibrium because, as you know, it has 25 axes of spin with 25 great circles that are pierced by these axes. And there were, I thought, enough orbits, or in my case, orbitals, with paired electrons in a line relationship in each great circle orbit, that I had enough orbits to describe the various atoms and their configurations. And this, as I mentioned, is an example of carbon, which is tetrahedral. And as you can see, there are these vertices. This is behind this vector equilibrium, and so it's in a dotted pink. But if you would join these vertices with lines, you would have a tetrahedron. And this is an exploded spherical version of this vector equilibrium. And you can see the various great circles that I used as orbital or, well, orbit in my case, lines. Now, of course, if it were a three-dimensional planar configuration, then we would have one electron here, here, and here to create a plane made up of 3 electrons. If it were just a 2 electron system, for instance, we would have one here and one here in an aligned relationship. For instance, let's take carbon, which would bond to 4 hydrogen to form methane. Now, this is the carbon atom in the center with 4 electrons. Carbon has 4 electrons. Now, hydrogen has only 1 electron. So, if these 4, 1, 2, 3, 4 electrons were that of carbon, then these places, the other 4 places, are vacant for each hydrogen electron to bond at those places. And so the next slide will show you in the next phase when this electron of hydrogen would traverse to here on the opposite side, it would become like so. So this would show the 3 original electrons of the tetrahedron with 4 electrons of the 4 respective hydrogen atoms. And these electrons are in motion, and so are these electrons of the carbon. And so going back, you would see that when the electrons of the carbon that were here move diagonally opposite to the other side, then we get that in the next phase. And that's how carbon electrons and hydrogen electrons are bonded. Basically, bonding in molecules occurs by the pairing of these electrons, positive and negative spins. So, as I mentioned earlier, the 4 diagonal bracings through the center of carbon in methane are the bonding vectors to attract the electrons of the hydrogen. And so, as I said, the interior bracings, the vectors, are in tension, while all the peripheral vectors are in compression. So it's this balance of just compression and tension members, positive and negative charges. And so you can see that basically the atom is a tensegrity structure by nature.
And our third speaker and panelist is Dr. J.F. Jim Nystrom from Big Rapids, Michigan. Dr. Nystrom is an advocate of using Fuller's geometrical and synergetic ideas to explain all aspects of the physical and metaphysical world. He holds 4 university degrees and has internationally recognized research accomplishments in statistical mechanics, computational electromagnetics, and cellular automata. He utilizes Fuller's synergetic geometry to create a computational theory of universe that in 1992 he labeled computational cosmography. In the computational cosmography, he utilizes Fuller's jitterbug idea, acting at all nodes of an evolving background IVM to model Wheeler's quantum foam ideas. So Jim Nystrom.
The overall idea is something I called computational cosmography back in '92. I read Bucky's book, Cosmography, and it reminded me of things that I had read like 6, 7 years before. Okay, well, so I'm going to go through a calculation that I did in '95. This is a tetrahedral fractal right here, and what had been done in statistical mechanics, they had just the two-dimensional, the planar model had been done, and they put spin variables on each vertice in the plane, and that's called the Sierpinski gasket. It's a pretty famous calculation. And I was a grad student in physics working with James Walker, and I said, well, what if I take the 3 planes and fold them over, because I'm familiar with Bucky's geometry. And so when you do that, and then if you take out an octahedron out of the tet, you know, I get 4, and you do it again, and you get this fractal. Okay, and I know it's hard to see here, but you put spin variables on each of these, and so this produced a two-dimensional renormalization group calculation. And it was actually the first two-dimensional calculation that admitted a finite field, where I could actually put in an H field in it. And so it was a pretty nice calculation, and it used some of Fuller's ideas. All right, so the next calculation I did, I bounced around in graduate school, got the master's in physics, then went over to electrical engineering to do my PhD, and I worked with computational E&M. I actually did other E&M calculations while a grad student, but the whole time I was working on this model here, on putting Maxwell's equations on Bucky's geometry. So real quick, this is the Maxwell's equations. This is a curl operator. It's a spatial operation. And so I can take these equations, and usually you break these down into x, y, z coordinates. But I went ahead and I broke it down into 6 vectors of the tetrahedron in there. So E1 through E6. Okay, so we all of us here know about the VE and then the IVM grid. Okay. Usually when I give this presentation, people don't know about that. Okay, so here's my vector basis. Okay, E1 through E6. The first time I did this calculation in 2003, I actually used quadri coordinates, different coordinate system, but since then I've put it onto the Cartesian axis. Okay, and so 6 vectors, and now we're all familiar with the 4 hexagonal planes. And what I'm going to do is I'm going to do a line integral around each of these 4 hexagonal planes, because the curl operator via Stokes' theorem, I can take the curl operator and it does a line integral, and so I just did that numerically. And what happens, it's quite beautiful here. Okay, so each of the 6 elements of the resulting curl are dependent upon 2 line integrals. Okay, and so here it shows it. This is a visualization of the vector curl. Each 2 that you do, you get a resulting vector right here. And so here the A and B planes get the E3 component. Over there's another view. And for me, this shows here that inherent in the vector equilibrium geometry, which I believe is the foundation on how nature works, electromagnetics, one of the most important forces in a universe, naturally decomposes onto this. Okay, and so this is just the spatial part. So I do that spatial part calculation numerically. Here's just some detail on calculating it. Of course, there's a lot of work to do that. And then For the time integration, I use a Runge-Kutta order 4. And let me just get to, here's what happens. I can make the E field into a tetrahedron. And so initialize the system and then start running it. I have a separate MPEG file, can maybe show later, but the system just flows right there on the grid, and depends how you initialize it. I can turn the E field into a tetrahedron here. And so I was really happy with this calculation there. Now the next thing I'd like to show is some recent work with some random walk stuff.
Our next speaker and panelist is Russell Chu. He's affiliated with Construction, RCHU, RCHU Construction, and Russell is from Seattle, Washington. And his presentation is on exploring the science of the IVM VE close packing in nature's design, the building blocks interpretation of the geometry of close packing of spheres. So, Russell.
Actually, I have done a lot of work with isotropic vector matrix, and what I did before was I realized. Maybe I should back up a little. I was looking at IVM as a coordinate system, so I was looking for some connection between the IVM and chemistry or crystallography or things like that. What I first realized was that even though Bucky didn't like the cube, there were cubical crystals. You know, one of them was salt, so the regular salt. And I started looking into the IVM. I realized, and Bucky has shown that two tetrahedrons make the dual tet is a cube, actually. So in looking for that, I realized that if you interpenetrate two IVM lattices or systems, coordinate systems, you will get all cubes. So you get a whole lattice of cubes. And then from there, I realized that you could have 4 different IVM lattices. And you could combine them. If you label them A, B, C, D, you could combine them to get a whole lot of structures in chemistry. And that is really the same thing as Arthur Loeb did with his modulohedra system, which he put inside of plexiglass tetrahedron and octahedron, he put a ball in the center, so indicating that there was another atom in there. So when I did that, what I realized that the IVM is only one part of what is possible with closest packing of spheres. There's the other one is hexagonal closest packing that people don't address because it's not so symmetrical. But you can also interpret it as combinations of tetrahedron and octahedron, except that they are stacked directionally. So, but a few years ago, about 8 years ago, I got a model. Somebody Tim Cox sent it to me. And it was model of spheres. And one had 13 of them, which was the vector equilibrium or cube octahedron, 12 spheres around one, right? What I realized was that there was another way of putting things together in this system. Well, the vector equilibrium one, the 12 around one, which was 13 balls, had one center, the nucleus, one ball in the center, and the other one had octahedron in the center, which matched what I was doing before, that there was 4 IVMs, and one of them had it was a cube octahedron, one in the center, and by volume, I have figured, I labeled A, B, C, D. The first one was a tetrahedron center, which would be something on the side like here. The other one's octahedron center, which would be here. And well, there's 2 tetrahedrons. So the black tetrahedron, and right here, and then the left tetrahedron, the white tetrahedron. One is,
can you raise that up?
Yeah, one is pointing up and one is pointing down. The white is pointing up and the black is pointing down. So I had told him, and that was the 4. And what I found out, it really surprised me. And what I found was that it was the tetrahedron itself. So here is, a tetrahedron. It's 4 spheres. And what happens here is it's all tetrahedrons. There's no octahedron in here. So I'm going to take this apart. So it's 5 tetrahedrons. So what is going on? This structure is exactly the same as this one. There's 4, but it's different. It has tetrahedrons and octahedrons in it. And that's where I realized that it was a matter of how you're interpreting this. And this one is using Euclidean geometry, and this one, it does not follow the Euclidean geometry. It's not all space filling. This one is all space filling, and this doesn't quite fill space altogether. So that's the difference, 74% and 100%. So that difference makes a lot of difference conceptually. It's very different concept. And there's a different geometry to it. And that was the exhibit I put in the Nature Lab. Because once I found out about tetrahedron, I realized that there is more to it. So I went back all the way to the 1 sphere. And you can see that from here you could do 2 spheres, right? It's a combination of 2 spheres, right, like that, building block wise. I think I'll leave it at that. So, all right.